All right, good morning, everyone. Welcome back. All right, so we have a new chapter. We're getting close to the end of the semester. So next week is our final week of instructions. So we're going to cover one more chapter next week, and that's about it. So in about 2 weeks from today, we're going to have our final exam. Let's see. All right, so let me open the, there you go. So these are the lecture notes that I have for this week. See, I want to make sure that sorry guys, give me 1 second. I want to make sure that I have that open so you guys can also see. All right, yes, I have that slides, PowerPoint slides for cosmology on Canvas. So if you want, you can just open it and kind of follow along. And I do have few slides here and there, a little bit different, but mostly, keeping the slides about the same. All right, so now let's then start with talking about additional properties of our galaxy and type of galaxy. So that's something we talked about. Hubble's big discovery. We'll talk about that in chapter 12. So then in this chapter here, we talk about cosmology. So we're going to talk about Olbers paradox, cosmological principle, and the story of the Big Bang. So at this point, we pretty much covered let's say the stars, and we covered galaxies and type of galaxies and all of those things. So we have very good understanding of all the different pieces of our within our universe. This chapter pretty much gives you sort of like the breakdown of, like, let's say in terms of let's say as a cosmology, which is basically a study of the universe from the very beginning until the very end, and every sort of like in between what's going on. So we're going to see that excuse me, we should be able to look at some of the answers, like, let's say what, how, when, in terms of what happened, how the universe was formed, when will universe end, if it will end, or when it started. So all of those type of things obviously are very important for astronomer and pretty much everyone else, right? So you want to know your sort of like, we know now more or less your place in the universe. So we know that we are on a planet Earth, which is in a solar system, which is in a Milky Way galaxy, which is part of a local group of clusters of galaxies. And that's basically, from that, just one cluster compared to many other clusters. So, and there are 100 billions of galaxies, each one containing over 100 billions of stars, and so on and so forth. So that's basically, we know our place. But then some other questions here is, why are we here? Probably, never, at least at this point, we don't really know the answer to that. Why are we here? Not only why are we here in terms of why there is a planet Earth or something like that. So those type of questions we were able to answer, right, more or less, because the galaxy is filled with the clouds of gas and dust, and clouds of gas and dust are raw materials for any type of future let's say star formation or star system formation. And when in a nearby star systems, some kind of big massive star that remember, they live very short life, eventually dies and collapses and explodes, that shock wave triggers then motion within the gas and dust, let's say, in different parts of the galaxy, and that starts formation of a new star system with the new stars and so on and so forth. So that's just basically mechanics of the star formation and things like that. But in terms of, for example, why is there life on Earth? Is there life on other places? That's something that we can, look at maybe in the next chapter. But this is mostly in terms of, let's say, where are we in terms of the history of our universe. So we can talk about how in the previous chapter we learned that galaxies are receding from one another. That means if galaxies are receding from one another, is it possible that if you kind of like rewind back time, we can see them originating from some point or something like that? So those type of things we can answer using science, right? Using mathematics, using the experimental data and things like that. And some of those things we're going to be able to see. So, obviously something like, Earth is let's say, on top of turtles. Well, we have to also talk about, or give, shout out to some of the other models that we have. For example, definitely there's really, let's say lately, especially the model of flat Earth or something like that. It's kind of gaining a little of, let's say, within such certain group of, let's say, citizens, like they kind of interesting way of, have a way of describing why they think Earth is flat and things like that. So at the end of the day, the science is basically something that you can come up with an idea, whatever you observe, and that idea can be put forth as a hypothesis, and then it can be verified. Then that becomes a theory, and that your theory can be then either become a law if it was, let's say, universal, or it can just more or less remain a theory until, more and more experiments verify your predictions. The same thing we're going to see in this chapter. Obviously, the astronomy is one of the hardest one to verify, because we're not like biology, where you can take a petri dish and grow let's say a bacteria culture and then see it basically the entire evolution of some kind of bacteria. We don't have that luxury, right? So we know that the shortest lifespan of any star is millions of years. That means we cannot just sit here and absorb a star from birth to death. We have to look at one star during the young star, then an old star, the one that is already dying, and compare and contrast. So basically look at, is something we observe here in our galaxy, which we can. Our telescopes allow us to observe things in our galaxy, like radio telescopes and so on and so forth. We have a good understanding of, some of the mechanisms inside our galaxy, because it's close. So we can look at, nearby star systems, try to find planets there, and exoplanet, let's say, a branch of astronomy is very active right now, trying to find planets around other star systems and things like that. But again, we have to get experimental data to come up with some kind of way of describing things. And obviously here, when we talk about cosmology, is one of the hardest one, because we're talking about billions of years, so what happened, like, let's say, billions of years. And it's one thing we're going to see is that universe is not static. It's not, forever. It's not constant. It's dynamic. It always changes. So it's sometimes even unpredictable. So that's why there are some theories, they are better than others. So when we're going to talk about, like, say, Big Bang theory, right? So at this point, all the evidence points toward the Big Bang theory. There are other theories that, let's say, we have, right, for the, let's say, origin of the universe up until, the concept of Big Bang theory was formed in 1930s and 1940s. So not even 100 years ago. Before that, we used to think that universe was forever and constant and never changing. So that means, not even 100 years ago, we used to think that. Now we think differently. We don't know what we will have in 100 years from now. That means, every time there's a new evidence, we modify. We don't change, we modify our understanding of the universe. So that's basically what we have for this cosmology. It's a very abstract, concept. You can't really have 100% answer of everything. We have something very close, but generally what we have here is evidence points towards certain things, and that's what we're going to pretty much talk about here. Go ahead, Anthony. You have a question?
How did they just this may be like a crazy question, but I feel like the Big Bang Theory is such a wild theory. Like, how do they just come up with that?
Yeah, so we're going to talk about that. So I don't want to let's say answer this question right now, because we will talk about that in this chapter. So I think the best way is to digest that material is go through some of the initial findings and things like that until we eventually get to that. But yeah, I mean, it sounds like a crazy idea, definitely, but I mean, a lot of things sound crazy, right? At some point when you talk about, let's say, if you go back several hundred years ago, the concept of electricity would have been crazy, right? Concept of flying would have been crazy, all of those type of things. So yeah, I mean, what technically could be a little bit crazy right now, or it was crazy in 1940s, 1930s. Not everybody actually accepted that, but pretty much nearly all the astronomers right now accept the Big Bang Theory, because the evidence points that because we talked about, right? So the galaxies are receding. Well, maybe they started from some kind of, beginning, right? So if they're moving away from each other, maybe if you rewind back, they will have some kind of, a beginning point or something like that. So yeah, we will be talking about that in this chapter, in the next chapter as well. So we'll cover those, some of those concepts, and hopefully by end of this class or by end of this week, right, you will have a little better understanding of the Big Bang Theory. All right, so but before that, so let's talk about a couple of other concepts that are, for example, Olbers paradox. So this is something that was, let's say, can be used to, I guess, provide some kind of proof for a Big Bang Theory, for example, because we're going to talk about, right, the Big Bang Theory is a theory where the universe has a beginning. Okay, so the universe has a beginning. So and this, for example, this paradox assumes that, let's say, what if there was no beginning? Okay, what if the universe was infinite? It was here for as the infinite amount of time. Yeah. So that means when you look at the night sky and you look at the stars and you look at everything around us, right? They should have been there from basically beginning of whatever, assuming let's say so this is the thing, like this concept of infinite universe. I mean, that means they were always there. There was no beginning. There was always there. So let's say, and they were there from extremely long time. But if that was the case, right? So then if the stars were there, then from a very long time, then our night sky would not be dark. So that means what we have here is, like you see, right? Let's say if you look at the forest, at some point you'll not going to be able to see anything else but trees, right? If it's a forest after forest after forest, that means if you look at the forest, that's what you will see. Same thing right now. If you look at the night sky, that means at some point all the skies will be filled with light, because I mean, there are stars everywhere, right? So remember, there are stars in our galaxy. There are 100 billion stars. Okay, if we take just our galaxy, maybe there would have been some dark patches, because stars are a little bit further away and things like that. But then if you consider the entire universe, 100 billion, let's say, galaxies with each 100 billion stars. And again, that's basically going with a little bit smaller number than, like, let's say, we're pretty sure it's more than that. Imagine, right? If we are eventually, see, one thing we learned last time was that the light takes a long time to reach us. So let's say right now, when you look at the galaxy far away, right? For example, Andromeda Galaxy is one of the closest galaxies to us, really, really close, but it's 2 million light years from us, which means the light takes 2 million years to reach us. Well, if there's a galaxy that is, I don't know, 10 billion light years from us, it means it will take 10 billion years for that light to reach us. But the idea here is that if all of those galaxies, all of those stars have been there for the infinite amount of time, that means eventually all those light would have reached us. And if we look at the sky, it would have been bright. So the night sky should be as bright as the surface of stars. Obviously, we don't see that. For example, this is sort of what we would have seen. Eventually, over time, all the light would have reached us, and we would have seen a night sky just like this. Okay, we would have seen night sky just like this. But obviously, we don't. Okay, so this is what Olbers paradox is. So the fact that the nights or the night sky is dark is because the universe maybe had a beginning. That means we didn't have a light. We didn't have the let's say, infinite universe, and the universe basically had a beginning. So we still have, stars and galaxies that didn't have time for their light to reach us, or basically, they didn't have time to occupy the entire, like, let's say, space of the universe. So this is, another, like, let's say, one of those paradoxes that, let's say, if there was infinite, this is what we would have absorbed. It's not. So maybe here's a possible solution. Doesn't mean that this is the only solution. There could be, I don't know, other answers, but at this point, this is one of the solutions that makes sense. That means if the universe has a beginning, then we can only see the light from galaxy that has time to travel to us since the beginning of the universe. Okay, so that's the best way, that we can describe why the night sky is dark rather than bright. And in a way, probably good for us, right? Who would want, a very, very bright a night sky like that? But in any case, so that's one, let's say, score for the universe to be finite rather than infinite. And there was a lot of, philosophical debates and things like that, because from the religious point of view, right, you want there to be, infinite. That means we've been here a long time and so on and so on. But then the scientific facts and things like that, point otherwise. Now, in terms of then what we have, so if we talk about, our cosmological principle, so we're going to talk about some kind of, a fundamental assumption that we have to make. So let's say, in terms of talking about the universe, we want this, universe is, homogeneous. So this homogeneity is basically describes how on the larger scale, the local universe has the same physical property. Okay, so meaning, let's say, whatever you talk about some kind of star in our galaxy, or some kind of planet in our galaxy, and you look at what's happening in our galaxy, absorb the planet formation, absorb the black holes, absorb the pulsar stars, and so on and so forth. So all of those things should be very similar to the data that you get if you, let's say, lived in Andromeda Galaxy and looked at, let's say, things in Andromeda Galaxy, right? So how the planets formed over there, how the stars form over there, how the stars die, and all of those things. That means homogeneity is that the local universe has the same physical properties. Also, the universe has to be isotropic, which means on the large scales, the local universe looks the same in any direction that one observes. Okay, so again, those two are very important because, see, the homogeneity allows us to study our galaxy, study our solar system, study our planets and moons right, in our solar system, and have an understanding of what let's say moon is, what the planet is, what is a rocky planet compared to the let's say Jovian or gaseous planet. And then we can look at other, let's say solar system, other star systems and other galaxies, and assume that things should be about the same, as I said, right? So that means, we don't go to Andromeda galaxy and then the laws of physics are completely different, right? So things, should be the same in our galaxy compared to other galaxies. That means universe whole, our universe should be homogeneous. And isotropic means that, let's say, it's pretty much going to be same thing for us as it would be for someone living in Andromeda galaxy, or someone living in, I don't know, like very, very far away galaxy. For them, the universe should be kind of like the view of the universe should be exactly the same as us. So that's kind of like one of the things we have. That means the local universe looks the same in any direction that one observes. Okay. So now that's kind of like, that's in terms of in any direction, it's kind of the same. All right. So in terms of then the third one, so this one sort of like, let's say, can change a little bit, right? So you can also have in terms of the infinite, non-changing, constant universe, and changing universe that, let's say, moving, the galaxies receding from one another and those type of things. So, sorry guys, give me 1 second. All right, sorry. All right, so what we have here is, as I said, right, so there were a lot of debates about is the universe infinite and static and never changing, or is it, or it is changing and receding or accelerating and so on and so forth. Obviously, the new evidence points toward the second one. So then what we have here is the number 3 says universality. And again, that's something I just mentioned, that laws of physics are the same everywhere in the universe. That means we can apply same, for example, Hubble constant that we talked about in the previous chapter to the planets, so to the galaxies that are billions of light years away from us, as well as a galaxy that is only, millions of light years away from us. That means everywhere in our universe, we can use that. Now, there are other theories in physics where there could be multiverse, where there could be other universes, like bubble universes. So that's another story, because that could be maybe another universe where laws of physics are completely different from ours. But this is just basically talking about our universe. And again, as I said, right, so within our universe, those 3, let's say, assumptions have to be more or less considered in order to have some kind of working model, being a Big Bang theory or something else. So as I said, right, so, even Big Bang theory, there were some skeptics, there are still some skeptics, and people, they are trying to find other ways of describing the, how the universe operates. All right, so from here, we talked about in terms of the what Edwin Hubble discovered. Remember that galaxies are receding away. And one of the things we have here is that's definitely was really important toward moving from infinite universe. So like, let's say the model, right? That means if the galaxies are receding from one another, that means, it's not constant, infinite, unchanged universe. It is changing, it is receding from one another. And this equation that we talked about was a relatively straightforward way of calculating the speed of galaxies. And further away the galaxy is from us, faster it is moving, because its speed dependent on the distance from us, right? So, for example, this particular equation just gives you I don't seem to be able to write on my PowerPoint slide. All right, so this VR, which is the recession velocity. So the recession velocity equals h, which is a Hubble constant, and it's a 70 kilometer per second per megaparsec. That's the h, that's the constant, never changes. But then d is the distance from us. So further you are from us, faster you are moving, because the speed is equals to this constant times your distance. So that means somebody that is twice as far, moving twice as fast, 10 times as far, moving 10 times as fast. So that's sort of like a linear relationship between velocity and the distance. So this was what Hubble discovered about 100 years ago. Okay, so that means this particular equation is also a point, or let's say an equation that can allow us to reverse everything, let's say backward a little bit. That means we can talk about, let's say, how long, more or less our universe existed. Because if we can assume that universe, basically galaxies are receding from one another, and we can find their speed. And there's this very, simple equation where time equals distance divided by speed. So if we do that, we take the time and say, okay, it's distance divided by speed. We can then calculate the time for our universe, basically when the everything kind of like started. It has, if it has a beginning, like the some of the evidence points out, right? That means this equation can be used to calculate that particular beginning. All right, so sorry guys, my PowerPoint slide froze. I need 1 second to kind of close that. All right, that, this one over here. All right, so and I should be able to write on that. Okay, perfect. Okay, so now in terms of then what we have here is we measure the recession velocity through the Doppler effect. Remember, Doppler effect was a technique that we use to figure out how the certain object, could be a star, could be a planet, could be a galaxy, right? Moving relative to us in a radial direction. Moving toward us basically is a blue shift, moving away from us is a red shift. So technically, the red shift is the galaxies, are moving away from us. So that means that's one of the things that we could use, to get that. All right. So now here's sort of like, let's say what we have. You walk into a theater, on the screen, you see car parts flying away in all directions. So I guess something like that, which means that if something happens, right, some kind of explosion, then, it does send out all the parts, right? If, let's say, car explodes, then all the parts move in every direction. So, and that's similar to what you can think of, right? Let's say the as a beginning, right? So that's kind of like getting closer to maybe there's a Big Bang, maybe there was some kind of explosion in the beginning. So that's the thing, right? So if you see all the parts kind of moving away from each other, you can, kind of like, let's say, rewind them back in time and see the point of origin. Okay, so that's kind of like the idea with this particular theory too, right? The Big Bang theory. And there were some recent developments that we're going to talk about to this motion of the galaxies relative to one another. But at this point, we're going to, keep this sort of like what we call classical, let's say a recession, speed. That means we're assuming that they're moving away from each other at the let's say at the speed that, let's say, increases with the distance. But once you calculate the speed of some kind of galaxy away from us, it moves at a constant speed. Okay, but if you look at the galaxy a little bit further away, it's moving faster than the previous one, but still moving at a constant speed. Okay, now because of this expanding universe, means that universe is expanding in all directions. So that's why it's important to understand that if you're somewhere else in the universe, you absorb exactly the same thing as we do. So that's why we can't say that we are somewhere in the center of the universe or at the edge or something like that. So there is a center for our galaxy. There are center for galaxies. There are center, for clusters of galaxies and things like that. But there is no such thing as center for universe, right? So universe is kind of like, from remember, so that isotropic, right? You see the same thing from all parts of the universe. So the idea here is, on a large scale, galaxies are moving apart with the velocity proportional to its distance. Okay, that means velocity. Remember, receding velocity equals constant times distance. So that's why we can say it's proportional to distance, because this guy here is just a constant. So further you are, faster you're moving. Now that means at some earlier time, galaxies were closer. Okay, so which means another equation for velocity is distance over time. So that means if you kind of rewind back, right, then you can say that, when time was small, right, then basically they were moving, a lower speed and pretty much were much closer to one another. That means space and the universe are expanding. So that's just pretty much basic, let's say observation, mathematical, equations, showing you that. Obviously, there had to be a experimental, proof for that, right? So when we observe the, things that we should be able to see, and that's, actually something that was not predicted to start with. We did not assume, we did not think that the universe is expanding. We actually got that as an observation first, and then Hubble was able to, from the experimental data, put forward this equation. So that's something also interesting, because physics and astronomy work sometimes where you can, imagine something, come up with an equations describing your idea, and then verify with the experiment, or you can, observe something and then try to describe that, try to explain that. And that's where the Big Bang is originated from. It's not an idea that somebody came up with. It's a necessity, because we see the universe expanding. That means we had to try to come up with an explanation why, and using the evidence, using the equations, using the data that we get, let's say the Big Bang was the most, let's say, logical, let's say the explanation of this. So in any case, so you can see, right? So what we have here is, when we talk about the space and universe is expanding, the galaxies themselves are not basically becoming bigger and bigger. So they're not necessarily expanding. So our Milky Way galaxy was not smaller, let's say 10 billion years ago, and now expanded, into something, a big balloon right now. No, the universe itself, right? The space itself is expanding. The galaxies, remains the same size. It just, the distance between them changes. So you can see, right? So if you look at the distance that they have relative to one another, now it's much more, right? So it's much greater distance. So between those two galaxies, much greater distance between these two galaxies, much greater distance between those two, and so on and so forth. That means the expanding universe, it's working on let's say the entire, system, not necessarily, galaxies or planets or stars are becoming bigger. Okay, so that's also something important to understand. So galaxies themselves are not expanding, but the universe is basically expanding. So the space between the galaxies and things like that. So that's what's basically that means galaxies just moving away from each other, right? So that's pretty much what the expanding universe describes. All right, so there are several analogies we can make. One is a loaf of raisin bread, where the dough is rising and expanding, taking the raisins with that. So you can see, right? So if you do that, let's say you started with let's say something like this, right? Much smaller size, loaf of raisin bread like that. But you put it in an oven, it starts, heating up, starts expanding. But doesn't mean that the raisins start becoming like let's say a blueberry size, or like they're not becoming bigger. So they just basically the distance between each raisin become much larger. Similar way, you can think of like, let's say if you have a balloon, or like let's say you have a small balloon, and let's say you put some stickers on it. Right, so let's say here's one sticker, here's another sticker, here's another sticker, here's another sticker. So then when you let's say blow the balloon, right, make it expand, then balloon can be bigger, but not necessarily those stickers, they don't become bigger, right? So they're still the same. It just there's their distance between one another, so like changes. So they're much further away from one another. So if you put a small sticker, the sticker is just same size, right? It's not going to like expand or something like that. So that's the idea. And so this is sort of like, let's say, what's also happening, because when you're absorbing the universe, so let's say you can say, right, so you're not necessarily looking at the universe from within the, let's say, balloon. What you're doing here is you're looking from the surface of the balloon. And that's kind of also, as I said, right, it's kind of abstract. So you have to kind of visualize that, which is not necessarily easy. So that's why there is no, let's say, center of the universe in a way, if you will talk about, right? So for example, if you live in this particular, let's say, sticker, right? Imagine you're an ant on that sticker. So for you can think like, okay, so what you only see the surface, right? So what you see here is that, this guy kind of moving away, maybe there's another one moving away, maybe another one moving away, but they're kind of moving away relative to you. But if you're right here, you see the same thing, right? Then all the other ones are moving away relative to you. So, but the only thing you can see is that the surface. So, right, so like, let's say from the surface point of view of the balloon, all of them are expanding, right? All of them are moving away from you, but you can say that what you see, how they move away from you, is exactly what someone else, some other ant and another sticker would see other, let's say, stickers moving away. So that's why it's a relatively, kind of like the abstract idea in terms of like, let's say, what do you mean there is no center? Sometimes students are, or sometimes everybody else, right? Astronomers are also kind of like not very. It's not easy to kind of visualize that. There are some, let's say, simulations and things like that that they can kind of show that. If I find one, I will post it on Canvas. But at this point, maybe there's this two, using the loaf of raisin bread analogy and the balloon analogy, let's say, should be a little more satisfactory in terms of understanding what's going on as expanding space, right? So not necessarily, you're looking at from within this, balloon, but from the surface of the balloon. All right, so that's why the necessity of a Big Bang. So it just, from the scientific point of view, right? So you have to come up with, especially when you absorb something first, it's sometimes a bit more difficult because you need to try to explain that. See, one of the things about science here is that if you have the theory first, then you know what you're looking for, then you can go and design, let's say, an experiment to verify that. But when you have, observation, then there could be, many different theories that kind of try to explain that. So then whichever makes more logical sense, whichever, provides a better prediction of the future events and things like that, that model then can prevail. So same thing right now with the Big Bang, right? So if galaxies are moving away from each other with a speed proportional to the distance, there must have been a beginning when everything must concentrate in a single point. And even this is a little bit, let's say, counterintuitive, because there was really no single point, right? So let's say, when Big Bang happened, it just happened, so like, let's say in space itself, not like a small space, and then everything kind of like started from there. So it just basically everywhere happened exactly same time. So that's why it's not necessarily an easy concept to digest. So let's say, all right, so you can think like the surface is finite but has no edge. So like, let's say, and what we have here is, what we can see here is like, let's say if you talk about universe, right? So the way universe started here, right? So it started like this, and then it started expanding. Okay, it started expanding. So the idea here is there's, there is no edge, there is no center and things like that. It's just everything kind of like, expanding like that. So that means what happens at the center, right? So just Big Bang. Now, I mean, we don't necessarily know exactly why it happened, why it banged, what banged, and things like that, right? But something happened, right? Some kind of we call it, inflation, right? So cosmic inflation. That inflation means that just things that start expanding, not necessarily inflation from the money point of view, right? So and basically that give rise to our universe, which then with time started expanding. Okay, so that means what we have here is conditions are basically in a way similar to what it was before, in terms of like, let's say, not necessarily during the Big Bang or a little bit after the Big Bang, because one of the things we know right now from the experimental data is that it was very, very, very hot in the beginning. So it took a while, maybe almost a billion years, so hundreds of millions of years for sure, for the universe to cool down, so that atoms can start sticking to one another and forming stars and galaxies and so on and so forth. So in the beginning, it was just a big soup of plasma, which means electrons and protons and things like that. It was too hot for them to form atoms and form matter. But at some point, right, they started forming, and the universe started shaping form, and then it starts expanding from that point on. Go ahead, Sanjay.
I'm not sure if you answered this already, but the universe is expanding, but what's it expanding into?
Excellent question. Technically, we don't know. There are a couple of theories that we have that in terms of, I guess, like two outcomes of our universe. One is it can expand forever. Into what it's expanding, I'm not really sure I can tell you that, but that one theory is that it can expand forever, which is kind of like counterintuitive, right? Because we were saying there is no infinite universe, but we're now saying that it can forever just expand like that. The other one is that eventually, just like you think of, like, let's say you have a ball, tennis ball, you throw the tennis ball out, you throw it upward, so it's going to go, slow down, stop, and the gravity eventually pulls it down, so it comes back. So we think that that can also be another outcome where the galaxies expand, because they were given during the explosion, they were given speed, and that they move with that speed outward, just like explosion, right? When explosion, they throw things away in every direction. But then eventually gravity going to slow them down. They're going to slow down. They're going to slow down. They're going to stop, and then they're going to collapse back down. So it's called big crunch. So that's another, let's say, model, another, prediction. So that means, is it going to be infinite expansion, or is it going to be, big crunch? There are kind of, two theories that are valid, and depends entirely on one of these things we're going to see, right? Depends on the density of space, density of universe. So if it's very dense, it has a high density, gravity wins, it collapses into big crunch. If it's going to be low density, then it's going to expand forever. And for now, it seems like more of the evidence points toward the first one, that is going to expand rather than collapse.
So right now it's just a matter of physics until maybe in the future we find out what it expands into.
Unfortunately, we will not be able to find out.
Oh, really?
Right. So our generation, that's not something
yeah.
will be. I mean, again, right? As I said, right? It's astronomy is one of those unfortunate sciences where it's very difficult to predict, especially sort of like a future, right? So it's especially like future of universe. So we are trying, and obviously we know much more than we knew about 100 years ago or 200 years ago and things like that. But still, for example, 200 years ago, what astronomers knew, well, for them that was the standard. That's what they thought. That's what's going to happen. But then 100 years later, they was like, okay, so you guys were wrong. This is what's going to happen. So now what we think, Big Bang and infinite, let's say expansion, maybe in 100 years from now, it's going to be, somebody going to discover something and they're going to look back and say, you guys were so wrong. This is what's going to happen. So that's science. So that's why we can't really predict anything with certainty, right? So there's so many uncertainties in science that, which is a good thing, right? That's what the science is, right? So new evidence, we have to modify our, understanding of things. So we cannot just hang on to, okay, I love this theory, I want to hold on to that, even if it's wrong. You can't do that. You have to accept that, if you have evidence without doubt that, your theory was wrong, you have to move on and accept it or modify so that it matches the new theory. So at this point, yeah, it seems like the evidence points toward the, expanding universe, forever expanding universe. But again, as I said, right, so we're going to talk about how, let's say, Hubble said that universe is expanding where the galaxies are receding at constant speed, which then at some point we were going to say, okay, so if they're receding, then they're going to slow down. If they start slowing down, then eventually maybe they will slow down to the point where then if the density high enough, they can stop and collapse back. So that would have been one of the evidences pointing toward maybe big crunch. But then one thing we're going to see is that the evidence point on the, completely on the other way around. We're not actually slowing down. We're going to actually moving faster. So that's something we're going to be looking at.
Yeah, that's interesting. Thank you.
Sure. All right, let me see. Alexandra wrote, what about the simulation theory? What do you mean by simulation theory? Like, let's say if we simulate something, is that what you mean by that?
I think we're in base reality and we'll be the first to create the simulation.
Oh, simulation theory, that we are simulation? Is that? Oh, I see. Well, I really don't know about. So basically, you're talking about matrix, right? So we are in a matrix. So that's I think whole another story. It could be. I mean, for example, I would not rule that out. So it's possible, just like right now, our understanding of creating video games, where they're very sophisticated, right? So how do we not, why won't we accept the fact that maybe we are a simulation created by even much more advanced, civilization, that for them creating simulation like we are, like this world is not a big deal. So it's possible. Definitely it's possible. There are physics theories too that, universe is just holographic and things like that. But, that's probably a little bit beyond the scope of this class. So I don't necessarily go and talk about that too much. But I don't know, like, let's say, I don't really know much about this simulation theory in terms of that, yes, I besides the fact that, I watched Matrix and all this stuff, and accept that it's possible, I would probably leave that, on the side, on the shelf until we know much more about that. I don't know. So let's say it just, to me, just like in Matrix, right? Eventually somebody will find out and something like that. So I don't know. It's possible, definitely. All right, guys. So let's continue with this. In terms of then one of the other evidences that we had for the Big Bang theory is that we were able to discover a radiation from the very early phase of the universe. And again, that was done by accident by two engineers, Penzias and Wilson. And they were fixing a satellite. Actually, I have a video that, kind of gives you a little bit of, a background information on them. So we'll just, wait for that. But the idea here is that in 1960s, this is already where the Big Bang theory was more or less accepted by astronomers as a, let's say, a theory of universe. So they were working on a satellite, on a radio satellite, not satellite, sorry, a radio telescope, and they were trying to clean a background noise. That means they were getting a noise that they wanted to kind of figure out how to get rid of. But unfortunately, that noise coming from everywhere, it doesn't matter which direction they would point, they would get that background noise, and they couldn't figure out what it was. But eventually, they sent that the data to astronomers to the nearby, if I'm not mistaken, I think Berkeley, and the astronomers were able to figure out that what they actually detected is the signature of a very early background, this cosmic microwave background, which is basically the information from the universe that was only a few hundred million years old. Okay, and they were able to discover that that background radiation has a temperature of 2.73 Kelvin, so roughly 3 Kelvin, which is extremely cold, obviously. So, but that cosmic background we call like CMB, so the cosmic microwave background, and hopefully this name also like let's say can give you a clue, microwave. Remember, microwave. Obviously, I'm not talking about device microwave or you microwave your food, but microwave as a device uses microwave radiation or electromagnetic light, right? Electromagnetic wave at the microwave frequencies and wavelengths. So we're talking about the microwave from very early part, the stage of the universe, and the light to be in a microwave range. That means it had to be stretched out quite a lot, and that's kind of what we have over here. In terms of this slide, kind of represents that. So after the Big Bang, the universe is too hot for matter to stick together. After a few 100,000 years, the protons then can capture should be electrons. This is known as a recombination. So photons can travel freely through space. Remember, photon is the particle of light. So then what we get here is we get the basic region of the universe soon after the Big Bang. So it's filled with hot, dense gas and radiation. It just basically it's about maybe dominated by radiation. Early universe was dominated by radiation. There was very little matter because electrons and protons, right? It did not recombine. It was too hot for that to happen. Remember, we talked about how electrons actually, if they gain energy, right, they would jump out of the atom. So it was so hot, they had so much energy that protons and electrons were separate. So eventually, when they couple, that they can form an atom, like hydrogen atom and then helium atom and things like that, right? But initially, the universe was pretty much all radiation, all pure, the radiation, what I mean is just pure energy, right? So then, so when we get the signature of that, so we do get this particular microwave background. That means, the light, that the radiation that we get is in microwave, which means it's redshifted. Okay, so it's a redshift. So recombination, right? Basically, there's a redshift by a factor of 1,000 when the temperature was 3,000 Kelvin. And what we have here is whole sky can be mapped. Let's say if you take right now a telescope and map the entire sky, you will get the signature of this this cosmic microwave background. That means you get this signature. That means it's everywhere in the universe. Okay, so every direction. That means this basically coming from all the sides. So the idea here is then we are getting the light from the most distant part of our galaxy. Okay, and that light has to travel a long distance to reach us. So then what we have here is that you can see, right, a distant galaxy emits a short wavelength photon toward our galaxy. Okay. The expansion of space-time, but because as it's moving toward us, space itself is expanding, right? So because of this expansion, so it stretches this photon to a longer wavelength. So initially when the wavelength is emitted, it's a gamma ray. Light, coming from, let's say some kind of star or galaxy always starts as a gamma ray. And it can break down into other things, but as the wavelength increases, it changes from gamma ray to X-ray, then to ultraviolet, then visible, then infrared, then microwave. That means what we have is that by the time it reaches us, it basically stretches all the way to the a microwave size. That means microwave has much longer wavelength than gamma rays and X-rays. Oops. So that's kind of what we have. That means when the proton arrives at our galaxy, we see it with a longer wavelength. That's what we call the redshifted, right? And the redshift that is proportional to distance. So that's why we can take that. We can then see how far away is the most distant galaxies from us. And how far away it is proportional to the time it was traveling. That means it's roughly, we can use this to figure out that the universe is roughly about 13, 14 billion years old, using this microwave background, because this is coming from at the most distant galaxies that were forming right after the Big Bang. That means that they were one of the first galaxies that were formed. Anyway, so let's put everything together that we just learned, and also some of the things that we're going to learn maybe Thursday. We can kind of maybe visually see everything in this next video. So this is about I think 10-12 minutes long. So we'll go ahead and watch this video and then finish the class with this. But this is you can see, right, it's mostly on cosmic microwave background, and this talks about this discovery, talks about the importance of this this CMB to our understanding of Big Bang and our ability to use that to let's say come up with a much better understanding, much better working model of this Big Bang. All right, so let's go ahead and watch.
In our previous videos on dark energy and dark matter, we've shown that only a tiny 5% of the energy density of our universe is made up of the ordinary matter we know on Earth. The vast majority of the universe, in fact, is dark matter and dark energy. Two entities which, at the present state of knowledge, we are unable in any way to reveal directly nor even to perceive. It's shocking having to admit that nowadays we don't know what 95% of our universe is, isn't it? How can we get these estimates? How can cosmology investigate the universe at such large scales? In the last decades, astronomers have discovered a fundamental element to study our universe: cosmic microwave radiation, CMB. What the heck is cosmic microwave radiation? Where is it? How was it discovered and when? What is it made of? This and other questions will be answered during this video. When general relativity was published, Einstein believed the universe as a steady system. However, very early, plenty of observations showed that the universe was not only expanding, but was even accelerating its expansion rate. In 1931, the Belgian physicist Georges Lemaitre went beyond and suggested that if the universe was not a static system, but was expanding, then by traveling back in time, it could be traced back to the moment of its hypothetical birth. He published these ideas in 1927 in the paper The Primordial Atom Hypothesis. Lemaitre's theory was named Big Bang Theory by the astronomer Fred Hoyle in 1949 during a BBC radio broadcast. Big Bang Theory was endorsed and developed by the physicist George Gamow, co-author in 1948, together with Ralph Alpher, of a paper about primordial nucleosynthesis. In the wake of this work, the same year, George Gamow, together with physicist Alpher and Herman, predicted radiation called cosmic background radiation. In other words, they argued that if the Big Bang Theory was right, expansion of the universe would have necessarily left the footprint of the very early universe into a microwave region of the electromagnetic spectrum. They predict the so-called cosmic microwave background, CMB, the echo of the Big Bang, the footprint of our universe. However, it took another 15 years to detect it. As often happens in science, in fact, many discoveries that will mark the future of later science happen by chance, almost incidentally. When this happens, it is said that everything happens out of serendipity, and this was also the case. In 1964, at Bell Laboratories in Crawford Hill, New Jersey, 2 steps from the University of Princeton, the physicist Arno Penzias and Robert Wilson were studying some radio emissions from the Milky Way using a Holmdel horn antenna. This is a large microwave horn antenna constructed in 1959 and previously used as a satellite communication antenna and radio telescope by NASA. Penzias and Wilson were calibrating a reception system to centimeter wavelengths when detected a background noise. At first thinking of some interference, they tried to eliminate any sort of the disturbance. Nevertheless, the signal remained steady with the same intensity. This was an omnidirectional background signal, not associated with any star, galaxy, or other celestial object. A faint background noise or glow, strongest in the microwave region of the radio spectrum. It didn't even depend on the direction of the antenna. They detected the cosmic microwave radiation that George Gamow, Ralph Alpher, and Robert Herman had predicted. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for this discovery. Let's go a little more into detail and try to figure out what exactly is CMB. This is radiation which permeates almost uniformly the cosmos. It is deemed to be the remnant from the early stage of the universe. That's why it's also called relic radiation. It's a very important source of information. At first approximation, CMB is isotropic and homogeneous. It is the same everywhere in the universe and in every direction. CMB has a perfect black body spectrum, the most perfect black body ever measured in nature. As a matter of fact, it has a nearly ideal Planck spectrum at a temperature of about 2.7 K, and according to Wien's law, has a peak in the microwave wavelength. A black body is an ideal object in thermodynamic balance at a certain temperature, which can absorb and emit all the electromagnetic radiation that it receives. This is very important because it indicates that when CMB was emitted, the universe was in thermodynamic equilibrium. CMB spectrum shows a specific pattern that fits very well a very hot gas pattern, expanding uniformly within the actual dimensions of the universe. CMB spectrum analysis has proven to be a mine of information about the early stage and the evolution of the universe. According to CMB Lambda model, the most upgraded cosmological model, cosmic background radiation was born in a very precise moment in the evolution of the universe, the recombination era, followed by the so-called decoupling matter radiation about 370,000 years ago. At this stage, the universe looks like an incredibly hot ionized gas plasma in expansion, made up of atomic nuclei of deuterium, helium, lithium, surrounded by electrons, charged particles, and photons in a primordial soup in thermodynamic balance. In these extreme conditions, temperature now is about 190 Kelvin. Binding of electrons with atomic nuclei cannot occur. Moreover, photons are continuously deflected and cannot travel significant distances without interacting with any particle. So radiation is somehow trapped in the plasma, and the universe in this phase is foggy. Let's imagine a little gate of a church seen from the outside. If it's tiny enough, it appears dark, even if the church is bright inside, because light cannot escape. As the universe continues to expand, it cools down until 4,000 Kelvin, when finally free electrons combine with hydrogen and helium nuclei and form neutral atoms. The recombination era begins 370,000 years ago and lasts for about 100,000 years. During this phase, the universe becomes more and more transparent to radiation, as photons no longer held can get away and begin to travel along with space. This moment is the decoupling of radiation from matter. CMB originates at this time. CMB detected nowadays comes from a spherical surface called the surface of last scattering. This surface represents the set of the point in space-time where decoupling happened. Therefore, CMB is considered the most ancient image of the universe obtainable. Before the last scattering, the universe was opaque and is impossible to receive any photon coming from a period prior to this event. The photons released during the decoupling era originally had a temperature energy of around 4,000 Kelvin. This would have been a visible yellow, orange, or white light. Since the universe has expanded since that moment over billions of years, CMB has now been redshifted from visible light to radio waves. microwave radiation corresponding to a temperature of about 2.7 Kelvin. Those same photons can still be detected as radio waves today and form the cosmic microwave background, and they provide crucial evidence of the early universe and how it developed. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. Experiments and measures over time have deeply investigated CMB, which has proven to be a veritable mine of information, through which our understanding of cosmic scales has made leaps and bounds, allowing us to deduce a lot of data about the deep structure of the universe. The first big project for measuring CMB was the Cosmic Background Explorer satellite, aka COBE. COBE was sent into orbit from 1988 to 1993 and had on board three main instruments: DIRBE, FIRAS, and the DMR. FIRAS, Far Infrared Absolute Spectrophotometer, was designed to measure the spectrum of CMB everywhere in the universe. DIRBE, Diffuse Infrared Background Experiment, was designed to gather data in the infrared band. DMR, Differential Microwave Radiometer, a microwave instrument to map variations in the CMB. For the first time, COBE measured the CMB spectrum with great precision. FIRAS gathered data for a period of more than 10 months, confirming that CMB has a perfect blackbody spectrum with a temperature of 2.73 Kelvin. Furthermore, DMR detected some extremely faint temperature fluctuations, 1 part in 100,000 only. So throughout the universe, there are colder and warmer areas of CMB. These variations are called anisotropies and represent a fundamental source of data. First of all, they constitute overwhelming evidence supporting the Big Bang as a cosmological theory, even if different processes can produce a black-body spectrum. No other model different from Big Bang has been able to explain anisotropies. That's why CMB, together with Hubble's law, are regarded as the best available evidence for Big Bang theory. The analysis of CMB and its anisotropy not only allowed to reconstruct of the processes that occurred in the universe during the era of recombination and decoupling, when it has been emitted, but made also possible to obtain important information on the structure and composition of the universe on a global scale, by examining the effects and interaction it undergoes during the intergalactic journey from the surface of the last scattering to reach up to us. The features of the universe on a global scale are described in theoretically models by cosmological parameters. In this sense, CMB has been and still is a crucial tool for estimate cosmological parameters and elaborating the cosmological model of the Big Bang. COBE was a very successful experiment, and George Smoot and John Mather, respectively head of DMR and FIRAS projects, were honored by the Nobel Prize in Physics in 2006 for their work. During the next decade, anisotropies were further studied by a large number of probes, either on the ground or through balloons. In 2000-2001 experiments, including the most important was Boomerang, measuring the angular width typical of anisotropies, together with other cosmological data. These experiments even get to assess that the geometry of the universe, finding that it has an approximately flat geometry. Originally known as the Microwave Anisotropy Probe, MAP, this uncrewed spacecraft launched in 2001 from Florida was renamed WMAP in honor of cosmologist David Wilkinson after his death in 2002. The WMAP objective was to better detect the temperature differences in CMB and to use them to measure the universe's geometry, content, and evolution. WMAP's measurements played a key role in developing, refining, and testing the current standard model of cosmology, the Lambda CDM model. Thanks to the measurements carried out, the precision and accuracy of the cosmological parameters were further improved. In October of 2010, WMAP spacecraft ended its mission and was substituted by Planck SATEL Light. Planck has been a space observatory built by the European Space Agency, ESA, from 2009 to 2013, which mapped the anisotropies of CMB at microwave and infrared frequencies with high sensitivity and small angular resolution. Planck had, in fact, higher resolution and sensitivity than WMAP. It observed in 9 frequency bands rather than WMAP's 5, allowing improved astrophysical foreground models. Planck has nowadays defined the most precise measurements of several key cosmological parameters, including the average density of ordinary matter and dark matter in the universe, and the age of the universe. It was renamed in honor of the German physicist Max Planck, who derived the formula for black body radiation. Planck was launched in May of 2009 and measured the CMB from 2009 to 2013 and aims to refine the measurements made by WMAP. In 2013, the European-led research team behind the Planck Cosmology probe released the mission's all-sky map of the cosmic microwave background. But the final papers by the Planck team were released in July of 2018. These are the most recent and accurate cosmological parameter measurements currently available. The map suggests the universe is slightly older than previously thought. According to the map, subtle fluctuations in temperature were imprinted on the deep sky when the cosmos was about 370,000 years old. According to the team, the universe is about 13.79 billion years old and is approximately flat. It contains about 5% of ordinary matter, about 26% of dark matter, and about 69% of dark energy.
All right, guys. So hopefully you learned quite a lot from this video. It went into quite a lot of details about cosmic microwave background and why it was so important for our understanding of the Big Bang. So I'm going to go ahead and stop today. On Thursday, we'll then continue with this. So this video already talked about some of the things we're going to talk about on Thursday, which is the shape of the universe. So it mentioned that some of those satellites, the experiments verified and proved that, or from the data that we gathered, right? So we were able to show that the universe was pretty much flat. So that's one of the things we're going to be talking about. And what are the other possible shapes of the universe? So we're going to talk about that. And, we're going to see that flat is the one that we got from the data. So the current understanding of our universe is that we have a flat universe and it's going to be, again, expanding forever. Right, but more next week, not next week, sorry, on Thursday, next class. So we're going to go ahead and stop. Have a good rest of the day, next 2 days. I'll see you all on Thursday, guys. Take care.
Thanks, Professor. See you.
Thank you, Professor.
Thank you.
Have a good day.
Thank you, Professor.
Take care, guys.